Okay, so as another example, the complex numbers is a one-dimensional commutative and associative division algebra over itself, since the complex numbers together with addition and multiplication is a field. And so the complex numbers is a complex Jordan algebra. So as another example, or counterexample in this case, the quaternions, considered as the algebraic extension of the complex numbers, is a two-dimensional vector space over the field of complex numbers, but is not an algebra over the complex numbers, since it is not true that for every three quaternions x, y, and z, and for any complex scalars a and b, that z times the quantity ax plus by is equal to a times zx plus b times zy. So notice in particular that the complex number a times the quaternion j is not equal to j times a, since the complex number a is of the form a sub 1 plus a sub 2 times I, where a sub I is a real number. And so a times j is a sub 1 plus a sub 2 times I times j, which is a sub 1 times j plus a sub 2 times I times j. While j times a is j times the quantity a sub 1 plus a sub 2 times I, which is a sub 1 times j plus a sub 2 times j times I, which is a sub 1 times j minus a sub 2 times I times j. Okay, so new definition. A Lie algebra, named after the Norwegian mathematician Sophus Lie, is a vector space V over a field F together with a binary operation which we denote with a bracket, which is a map of ordered pairs of vectors back into the set of vectors, so it is a form of multiplication, of vector multiplication, and this bracket is called the Lie bracket. Such that for every three vectors x, y, and z, and for every pair of scalars a and b, the following are satisfied. The first property is called bilinearity. Of the Lie bracket, that is, the bracket x ay plus bz is equal to a times the bracket xy plus b times the bracket xz, and the bracket ay plus bz and x is a times the bracket yx plus b times the bracket zx. So notice that if the Lie bracket satisfies the property of being bilinear, then this is the property which makes it an algebra over the field F. The second property that needs to be satisfied by the Lie bracket is that it needs to be an alternating operator. And this means that the bracket xx is the zero vector. And the third property that the Lie bracket must satisfy is called the Jacobi identity. The Lie bracket of x and the Lie bracket yz plus the Lie bracket of y and the Lie bracket zx plus the Lie bracket z and the Lie bracket xy must sum to the zero vector. Okay, before we look at an example of a Lie algebra, we need to establish a lemma, and so first we need to recall a Kronecker delta and permutation symbol. So recall that the Kronecker delta, delta sub ij, is equal to 1 if the indices are the same and 0 otherwise. And recall that the permutation symbol epsilon sub ijk is equal to 1 for even permutations of the integers 1, 2, and 3 is equal to -1 for odd permutations of the integers 1, 2, and 3, and is equal to 0 if there are any repeated indices. So now we consider an identity involving the product of two permutation symbols. Where one index value is fixed, in this case the index I. This is equal to delta sub jm times delta sub kn minus delta sub jn times delta sub km. So first notice that if I is equal to j, and similarly for any repeated index, we have epsilon sub I k times epsilon sub I m n is equal to delta sub im times delta sub kn minus delta sub in times delta sub km. So on the left-hand side we have 0. And on the right-hand side we have non-zero values only if I is equal to m and I is equal to n. And so we have delta sub I, delta sub ki, minus delta sub I, delta sub ki, which is 0. Now if the indices jk are equal to the indices mn respectively, then the two permutations are identical, and so we have the quantity epsilon sub ijk squared is equal to delta sub jj times delta sub kk. And so on the right-hand side we have plus or minus 1 squared is equal to 1, and 1 is equal to 1. Now if the indices j and k are equal to the indices n and m respectively, then we have epsilon sub ijk times the negative of epsilon sub ijk is equal to negative delta sub jj times delta sub kk. And so we have plus or minus 1 times the negative of plus or minus 1 on the right-hand side. And on the left-hand side we have, on the right-hand side we have negative 1. And so whether epsilon sub ijk is 1 or negative 1, on the left-hand side we have negative 1, and so we have negative 1 is equal to negative 1. And so this is a true identity. So next we prove a lemma. Let x, y, and z be three vectors in the coordinate space R3. Then the triple vector product, x cross the quantity y cross z, is equal to the scalar x dot z times the vector y minus the scalar x dot y times the vector z. So proof. The ith component of x cross the quantity y cross z is epsilon sub I j k x sub j, and the kth component of y cross z. And so this is epsilon sub I j k x sub j, epsilon sub k m n, y sub m, z sub n. And so we have epsilon sub I j k times epsilon sub k m n times x sub j, y sub m, z sub n. Now the permutation k I j is the same as the permutation I j k, and so we have epsilon sub k I j, epsilon sub k m n, x sub j, y sub m, z sub n. And so this is the quantity delta sub I m times delta sub j n minus delta sub I n times delta sub j m times x sub j, y sub m, z sub n. And so we have delta sub I m times delta sub j n, x sub j, y sub m, z sub n minus delta sub I n times delta sub j m, x sub j, y sub m, z sub n. Now in the first term, we have non-zero values only if I is equal to m and j is equal to n. And so that forces the y component to have the index I, and the z component to have the index j. And so this is x sub j, y sub I, z sub j. And in the second term, we have non-zero values only if I is equal to n and j is equal to m. So this forces the y component to have the index j and the z component to have the index I. So we have x sub j, y sub j, z sub I. And so we have x sub j times z sub j times y sub I minus x sub j times y sub j times z sub I. The product x sub j times z sub j is the scalar x dot z times the ith component of the vector y minus the product x sub j times y sub j is the scalar x dot y times the ith component of the vector z. And so we have that the product x cross the quantity y cross z is equal to the scalar x dot z times the vector y minus the scalar x dot y times the vector z. Okay, so now we can show that the vector space R3, the coordinate space R3, where the Lie bracket is defined to be the cross product, is a Lie algebra. So proof. The Lie bracket of x and a times y plus b times z is the product x cross a y plus b z, which is the cross product of x with the vector a y plus the cross product of x with the vector bz. And this is a times the vector x cross y plus b times the vector x cross z. And so this is a times the Lie bracket xy plus b times the Lie bracket xz. Now the Lie bracket ay plus bz x is the product, the cross product of the quantity ay plus bz times or cross the vector x. And so this is the vector ay cross x plus the vector bz cross x, which is a times the vector y cross x plus b times the vector z cross x, which is a times the Lie bracket yx plus b times the Lie bracket zx. So the Lie bracket does satisfy bilinearity. Now the Lie bracket of xx is the cross product of the vector x with itself, which is the zero vector, and so it is an alternating operator. Now the Lie bracket x and the Lie bracket yz is the triple vector product x cross the quantity y cross z, which is the scalar x dot z times the vector y minus the scalar x dot y times the vector z. The Lie bracket y and the Lie bracket zx is the product y cross the quantity z cross x, which is the scalar y dot x times the vector z minus the scalar y dot z times the vector x, which is the same as x dot y times the vector z minus y dot z times the vector x, and the Lie bracket z and the Lie bracket xy is the product z cross the quantity x cross y, which is the scalar z dot y times the vector x minus the scalar z dot x times the vector y, and this is the same as y dot z times the vector x minus x dot z times the vector y. And so the sum of these three Lie brackets is x dot z times y minus x dot z times y minus x dot y times z plus x dot y times z minus y dot z times x plus y dot z times x. And so the sum of these Lie brackets is the zero vector. And therefore, the coordinate space R3 with the Lie bracket defined as the scalar, or rather the cross product, is a real Lie algebra. Okay, so we'll end here for today. Next time we will continue with group theory. So I hope you have enjoyed the 16th lecture. Thanks for watching.